Yeah, so Lightning is a library that Mathieu Blondel started 4 or 5 years ago, and I recently joined the development, at least a bit less than 1 year ago. But since I live in Paris and he lives in Kyoto, sorry, it seemed more reasonable that I presented. But the credit actually goes to Mathieu Blondel. So since we're at PyData, I thought I should start with some data. These are the lines of code inside scikit-learn since the beginning up to last year. And actually, this has improved thanks to Arthur. But well, the absolute numbers are not important because actually most of it is generated C code from the Python. But what's interesting is the trend, that the code has not stopped increasing since 2010 up to now. So how does this model work? Well, this model continues to work mainly because the maintainers are very aggressive into what gets in and what doesn't. So they've done an amazing job at saying no at what people propose. So I don't know, 8 out of 10 pull requests get rejected or severely modified, which with very clear guidelines. And some of those guidelines are no new algorithms. So I think it's at least 5 years since publication and 200 citations. So only classical kind of generally useful algorithms get into scikit-learn. So this is a very hard constraint. It's great to make a package that's of general interest and that's maintainable over time, but might not fit everyone's user case. For example, I work in research and we have to continually bench ourselves against very recent methods. So for us, it's kind of important sometimes to have the latest algorithm implemented. So my point here is that scikit-learn is great, but does not cover all user cases, and one of these user cases is having very recent algorithms. In particular, in my user case, it's for large-scale optimization. And this is where Lightning comes into place, in that it tries to complement scikit-learn with things that would not be accepted by scikit-learn, such as very recent algorithms that are published like last year or even more recently. Okay, so the goal of Lightning, as I said, is to incorporate recent progress in large-scale optimization into a package that's scikit-learn compatible. I'll talk a bit more about what does this mean. Of course, since we're talking about large-scale optimization, the goal is to go faster than classical algorithms on data sets that are very large. One thing that was important from the beginning is to support both dense and sparse inputs, because the package was started with the main application at the moment was text, learning and predicting models of text. So that's a natural user case for sparse inputs. And also, there's a strong emphasis on structure sparsity that I'll comment more on that later. On the technical side, it's a lot of Python code. There's a bit of Python for computationally demanding parts, and we also use some infrastructure of scikit-learn. Okay, so my first point was that it's scikit-learn compatible. What does that mean? Well, let's see. How many people here have used scikit-learn? Okay, almost everyone, great. So if I say that my model implements a fit and a predict, you know what I mean. So I think that's incredibly powerful, and the main contribution of scikit-learn is not that it implements a lot of methods, which it does, but it provides some sort of unified language for machine learning algorithms. And Lightning kind of embraces that. It follows the scikit-learn API, and it feels and looks like a scikit-learn object. So in practice, if I guide you a bit through this example, what I'm doing at the beginning is just loading some data. Then I'm constructing a classifier. Here's called CDC classifier, doesn't really matter, with a bunch of parameters. And then I'm calling a fit method and a score. You've never seen scikit-learn code, but most probably you know what this code does. And one of the advantages of this is that it behaves like a scikit-learn object. So if you have a big pipeline which is doing, like in this talk we saw before, doing feature selection and then model selection and then God knows what, then I can just replace my SVM by an object in Lightning and my pipeline will still work. Okay. So I mentioned that the user case for Lightning is in large scale optimization. What does this mean? This is a bit ambiguous because data can be large in many different ways. For example, so we tend to represent data as a matrix in which you have the number of samples as rows and the number of columns, commonly denoted P. So you can have a lot of samples, like it happens in computer vision, where you have labeled images, and modern data sets can have, ImageNet I think was 12 million around. So a lot of samples. In advertising also you have problems where the number of samples goes beyond millions or billions. Okay, and there's another use case that's a bit different, in which the data can be large, but not necessarily because you have a lot of samples, but because you have a lot of dimensions. So think of it in neuroscience. You have problems in which you don't have many samples because you don't have many subjects in your study, but you have a lot of dimensions because there's a lot of variables. Okay? So I'm going to start first, talk a bit more about the large sample regime. So the problem in this case with standard algorithms is that they, standard algorithm like gradient descent, etc., is that at each iteration they need to go through the entire data set. So this, of course, can be very, very problematic and very slow. So what seems to be the trend right now is to go to simpler methods such as stochastic gradient descent. And in stochastic gradient descent is a classical method from the 50s, but in recent years there's been many variants of stochastic gradient descent that have been published in the literature, and in most of them we've implemented them in Lightning. So these methods have names like stochastic variance reduced gradient, stochastic dual coordinate ascent, stochastic average gradient, etc. So actually stochastic average gradient, one of them is implemented in scikit-learn. It was first implemented in Lightning and then it got ported to scikit-learn. But still in Lightning we have many others which can be useful just to have more, or if you're interested in comparing, and also because the one in scikit-learn does not support so many options as maybe the others in terms of penalties, etc. Okay, so at the right you see a graph that people in optimization like very much, in which you see essentially how fast the method converges. So each line represents how far I'm from the optimum versus time. So what you want to see is things going down very quickly, going to the optimum very quickly. So stochastic gradient descent, that's a classical method, tends to go down very quickly at the beginning, but then go very slowly, while these kind of modern variants of SGD tend to go down quickly at the beginning and then still go down very fast. So just to have an idea, the one implemented in scikit-learn would be this one, SAG, and in this particular problem there's also others that seem to do slightly better. Okay, another area where there's interesting algorithms in Lightning is in the setting of a large number of features. So Just like before, standard methods tend to, at each iteration, go through all the features. So all the columns of your data matrix. And of course, if you have a million of such dimensions, you want to avoid to do that. And one way to avoid to do that is so-called coordinate descent algorithms. So these algorithms are, of course, very efficient also if you have sparsity in your columns, meaning that a lot of them are 0. And this is a similar plot as I showed before from our paper by Mathieu Blondel, showing what's called block coordinate descent. So it's a kind of a generalization of coordinate descent for sparsity in like doing coordinate descent but through groups. And as you can see, of course, this is much more efficient than other classical algorithms like FISTA, which is mostly a gradient descent-like algorithm. Okay, I said that Lightning also supports, well, aims to support more structured sparsity. So I don't know if you're familiar with the concept of sparsity in statistics. It's a very powerful concept. It essentially means that you want to find the best model that has as many zeros as possible in your vector of coefficients. And why you want to do that is because having a lot of zeros means that your model is simple, and sometimes you want to have a simpler model because you want to interpret it, or because your problem might be ill-conditioned or undefined, etc. Well, and in scikit-learn, there are many methods that support this kind of sparsity concept through the keyword penalty L1. And in Lightning, we take this concept a bit further in that we add support for other forms of sparsity that are generalizations of the classical concept. So for example, group sparsity, which means that you want to be sparse, but not on every feature, but like by groups, you want groups to be either 0 or non-zero. Total variation, called a fuse Lasso. So in this case, you want to be not sparse, but piecewise smooth. So this, for example, is an example that got merged a couple of days ago. So in purple, there's a ground truth, there's a vector that has this piecewise constant shape, and you observe some data that is generated by the signal, and you want to recover the original signal, so it's a kind of a inverse problem. And if you just use sparsity, then like penalty L1, then you would have some zeros, but it would not. It would be kind of arbitrary. It has no notion of a spatial smoothness. While in this case, for example, this prior of total variation would be what you want. And we see here the green one. It's the method that uses this penalty. Okay. There are other forms of sparsity, like penalizing the trace norm, that is very much used in recommender systems because you assume that your matrix is of low rank, etc. Okay. Okay, so I've talked a bit of what's in Lightning. Now, what does the code look like? I'm going to compare it a bit with scikit-learn. So the philosophy is a bit different, even though I've said before that both objects can be mixed. It's just the syntax of how you create the objects is a bit different. So in scikit-learn, when you create a classifier, the name of the object defines what is the model. So if you create an SVM, then it's going to be, you're going to call an SVM. And what algorithm does that use in order to estimate the SVM? Well, usually there's a keyword solver that tells you what is the algorithm that it's using. In Lightning, because it's much more focused on the optimization, it does the other way around. You kind of construct your object telling him, okay, I want to use this algorithm, and then what's the underlying model gets specified by telling him what's the loss for. So if it's a logistic regression, then you would create almost any algorithm, but then tell him to use the log loss function. Okay, so contrary to scikit-learn, it's an API based on algorithms and not on models. And why this is important, at least for my user case, is because it allows a somehow more natural way of changing the model. So once you have the algorithm, you're very free to change what's the loss function if you have a strange prior because, I don't know, you like Laplacian loss functions, then you can just give him your own Laplacian loss function. Okay, so that's the user case, to be able to just choose the algorithm and tell him what is your loss function and also the penalty. Okay, so future challenges, what we'll be working on in the future. So one thing that we're thinking about, also because it matches my research, is to have more methods that are parallel. So scikit-learn, you have many models. So the parallelism you have is mostly, for example, on cross-validation faults, so on things that are naturally then can be naturally run in parallel. We'd like to have algorithms that can be run in parallel, such as stochastic gradient descent, but in parallel. And there's been, it's a hot topic right now in research, how to run these algorithms in parallel, and we're having quite amazing results in this respect. So for example, here I'm plotting the same curves as before, how fast a method goes. So in thick lines is for one processor, and in dashed line is for 10 cores. So you see a quite impressive speed up. It's not a tenfold speed up, as might happen for hyperparameters, but this is just one model, so it's much more challenging to parallelize. But let's say that you can have a 6-7 speed up on a 10 cores, which is already quite good. And of course, the next, so all the algorithms that are in Lightning, well, some of them are very efficient, but they still require the data set to be in memory. In theory, most of these algorithms could run out of core, so with the data set on disk and just loading chunks. There's the algorithms, there's the good abstractions, but it's not implemented. That would be also one thing to look out in the future. Okay, so recently, me and other developers from scikit-learn, we started a project called scikit-learn Contrib, which aims to be kind of satellite projects of scikit-learn that implement more bleeding edge algorithms that cannot go into scikit-learn, but are still scikit-learn compatible and would like to benefit from this increased visibility of being close in some sense to scikit-learn. So there's a GitHub organization where there's already 2 projects. Lightning was the first one, and now there's another one called PyEarth that joined, and I expect many to join in the future. So the requisites to enter in this sort of organization are to be scikit-learn compatible, meaning to have a similar API, of course to be documented, and to have a reasonable test coverage. Okay, so thanks for your attention. That's the URL for Lightning, and also we're hiring. So if any of you want to work on large-scale optimization, drop me a line, come talk to me. Thanks.